Okay, I think yes, I think recording is here, and now I can. Okay, please do let me know. I want to begin the class now. Do let me know if you can hear me. Can somebody unmute and let me know if they can hear me before I begin the class? Hello, can you hear me? Please confirm that you can hear me. Kende. Okay, thank you so much. Okay, so I'm going to begin the class. All right, thank you so much. Thank you. Okay, so this is Dr. Rinkelawa speaking, and if you were in class last week, we met, and I introduced the first topic, which is third program concept. The second topic will be the design of the simple CPU, peripheral devices, memory and storage devices. I kind of covered the basics of all of this, of the third program concept itself, and the devices that a typical computer is comprised of, and I shared the reason why it's important for you to learn this. What I said was that for you to improve upon existing computers, for you to improve on anything really, you have to have a very, very good knowledge of that, of the workings of that thing. So now we're talking about computer system. You have to have a very good knowledge of the computer system. Hence this topic, introduction to digital computer systems. So it is when you have a good knowledge of computer systems that you can begin to design something that would be an improved version, that you can begin to innovate. It is when you have a very good fundamental knowledge. So we're going to start with third program concept. I already talked about this in detail in the last class. I've sent these slides. I've already posted it to the Google Classroom. I've added you guys to the Google Classroom that I'm sharing. But if it's not, then you should probably quickly go download the slides so that you can follow as the class progresses. So the objectives of this particular class is for you to be able to understand the concept of a black box. And when we say black box, we are talking about your computer system as a whole. So we are talking about, all the parts that are connected together to make it a whole unit. You know how you don't really see the internal workings? That is there, hence the term black box, when you don't really know what's inside. So you want to know what is inside and how they are connected together. So at the end of this class, you should be able to define the von Neumann model and its concept and its components. So if I ask you what is the concept of von Neumann, what is the von Neumann model, you should be able to explain it to me. You should be able to use diagrams if necessary. If there are some illustration that you can do to explain it, you should be able to do that in your exam. So you should be able to understand the terms, third program concept. So if I ask you to define or describe this term, you should be able to write something down from your understanding. It doesn't have to be word for word. You don't have to cram. All you need to do is to understand this. So to buttress your understanding, I've also attached 2 separate YouTube videos that I believe breaks down the whole concept into simple terms that you can easily grasp from, I don't know where you're coming from. I don't know what you already know, but if you watch those YouTube videos, you're going to have a better idea of all the terms that you'll be hearing in this course, not just in this course, and as you take other computing courses. So you should understand the sequential execution of statements in a program. I briefly described this using real life examples in the last class, how different statements can work together for you to achieve a certain purpose, which is what the computer is about. So if you pick a computer to do anything, it means that there's something you need to achieve and you're using a computer to do it. So you need to understand the sequential. You know what sequential means? It means a step-by-step progress. Step-by-step way in which you are able to get whatever it is that you want to get done. So that should be possible. You should be able to, you should understand that at the end of this class, and you should be able to explain it if you are asked. So you should also be able to name the components of a computer hardware, software, and and the data. Okay, so now we're going to talk about, the computer as a black box. So this is a data processor model. Basically, a computer cannot work without data. So that is the work of a computer. It's supposed to, manipulate data for you. So you are bringing something and then you want to get something, or you need something. Of course, bring an instruction or whatever it is in form of the data. So you are bringing it into the computer as inputs, and then oh, okay, at the end of the day, you're going to get your output, which is what you expected in the first place. So that is the whole concept of a computer, and I'm sure you've learned that from primary school computer classes. So the computer is an electronic machine that accepts data, processes it, and then gives you a result at the end of the day. So that is still the whole idea of this course of this introduction to digital computer systems. Is just that we are trying to go into more detail, because you're no longer in primary school. This is not basics of computer anymore. So now you are going to graduate as an engineer or a computer scientist. So you need to go in depth into, okay, so how does this input enter the computer? How does this processing work? And then how does the output come about? So now they are going to start to learn all of that. Like I said, if you watch YouTube videos on your own on different concepts, you would understand better. And then when you come to class, a class is just maximum 2 hours at a time. So sometimes there's little that can be taught to you in a class, and that is why the university is slightly different from secondary school, right? That is why it's called a lecture. It's not a lesson. So a lecture, is supposed to give you, the general idea, and then all the in-depth parts of, the learning, you're supposed to find a way to, study on your own and, get it done. And then if you have any issues, you bring it back to the lecture hall, and then you can ask questions. So, let's get on with the class. So the computer now. The computer can be described as a programmable data processor model. Programmable, when something is programmable, it means it can be manipulated. And when something is a data processor, it means it can use data, it can process data. So that is all you need to know about computers. So computers are general purpose machines. They are general purpose computers where the computer already has a specific program. So all you need to do is bring what you need, bring your inputs, and you get the output. The whole process is rigid. It's just one thing that it does. So that is what a general purpose machine is. For instance, an ATM machine is a general purpose machine because the only thing it's there for is for you to withdraw money and do computing transactions. You can't say, oh, because an ATM is a computer, I want to use it to calculate something quick. Or I want to use it to, whatever it is, what does your computer, I want to use it to quickly and print something. That doesn't happen because it has only one program that has been, installed on it. That's the only thing it can do for you. So, yeah, computers, this is called a general purpose machine. So I'm sure you can think of other examples. If I say, okay, what other examples of general purpose computers can you think of? One? I'm sure you can think of one or two. So what's a program? So if you say a general purpose computer has just one program on it, what do we mean by computer programs? So before I proceed, can somebody on mute and let me know if you are hearing me loud and clear? I want to know if you're following me, if you're hearing me.
Yes, ma'am, we are.
All right, thank you so much.
We can hear you, ma'am.
Oh, great. Okay, so we're talking about programs. So what's the program? I'm sure you know programmers. You might be a programmer, so this should be easy for you. The program is a set of instructions that tells the computer what to do with the data. So it is written in a computer language, and that's why you might be a programmer. You might know Java. Somebody else might know C Sharp, and so on. Python. You already know the different types of computer languages. So the simplified definition of a program is just something you write in a certain language so that whoever is interacting with it would understand, okay, this is what you put in, and then the computer understands what you're asking and then gives you exactly what you want. So A computer is a set of instructions that tells a computer what to do with data. It's sorry, a program rather, and it is written in a computer language. So there are computer programs. There are some computers that have the same program, but it will have different data. So I'm sure, I think we can say that an ATM might fall under this category where the system is already there. You bring your own input, so to say, and then the processing that gives you whatever it is that you requested for. A calculator now can be an example. So you similarly you want to add 3, 12, 8, and 22 together. That is what you want. That is what you are bringing. And then somebody else, Damilola, is bringing 14, 6, 8, 12, 3. To do the same thing. You want to solve it, or you want to add it, or you want to multiply it. So in this case, you can say we have a computer with the same program for different data. On the other hand, you can have a system where, or a program where it's the same data, but you have different programs. So you can say, I'm bringing the same data, but I want to add it, and I want to sort it, and I want you to help me identify what the smallest is. So now this is where things are. Most computers these days do so many things in one whole box, right? You can do different things. So, for instance, your phone can do so many things, and that is how you can see that computers are evolving. So somebody can say, oh, tomorrow we are going to, before smartphones were limited. You could only do maybe like 3 things. Now you can do like 20 things. Now there's a compass on your phone. Now there's temperature sensor. Now there's so many other things on your phone that used to not be possible before. But by the time you study computers, and by the time you study their components, you'll be able to do some innovation, test some things out, and produce something new. So now let's go to the von Neumann model. I spoke about von Neumann in last class if you were there. And I told you that, there's a man named John von Neumann, and he came about with the concept that, okay, why not let us have something called stored program concept, where we would have what now, data and instructions stored together in memory. So the computer is there. You don't have to go and bring in data from outside to feed it into the system, and then you get an output. Let the data be there. Let the instruction be there. So von Neumann model now. So every computer today is now based on that idea. Before this concept, computers were run in various other means. Which I'm going to give you as an assignment at the end of the class. I'm going to talk about the history and evolution of computers. So you can have a good idea how things were before this particular concept that we are talking about. So in anything, before this, before that, there will be something, there will be a way that things used to be. So let's focus on von Neumann model for now. So von Neumann model is based on 3 major ideas, and that is that every computer has 4 subsystems, and every computer runs what is called stored program concept, which is what I explained in the last class. And then in every computer, there is a sequential execution of instructions. So if you think about this thing, it's really, really simple. So we'll take the first idea first, which is the 4 subsystems. So von Neumann says, okay, let us have 4 subsystems. Let the first one be memory. Let the second one be arithmetic and logic unit. And then let the third one be control unit. And then the last unit, let it be the input and output to the peripheral. Okay, so let's talk about the first one, memory. So we're talking about the fact that, okay, we have a memory where we are going to be storing programs and data inside that memory. Remember when I said that the stored program concept. This is exactly what the stored program concept is like. Put the program. That's the set of instruction, right? Because we've talked about that. And then put the data that people will be supplying, or that whatever other system will be supplying, put it together and let it live inside that computer memory. So that's the first of that takes place. So this is where if you want to do some arithmetic operation like addition and subtraction, if you want to do some logic operation and or okay, so if I want to pick this person and this person, well, you can decide that, or I want to pick either Damilola or Timileyin, or either Samuel or Timileyin. You can give that instruction, or you want to say, okay, I want Alex and Nete, Arafat, and Small Bome to go this way, and if they go 20 minutes after, I want Emmanuel, Esteliose, Ezekiel, Iyanu to follow. These are logic operations. So logic, things that like conditions basically. Like, okay, so if this condition is let this happen, and then let this happen. If you're a programmer, you know your what if control statements and all of that. This is where this is the subsystem of the computer model where all these operations happen. And then we have the control unit, where the whole basically the whole instruction, the processing, this is where it happens. And then we have the IO where, okay, so this is the mode of input. Are we going to type it? Are we going to use the, I don't know, how do we want to give that input into the computer? So, and then also, how do we want to get it? Do you want it to display on the screen? Do you want it to be printed? Do you want it to, be forwarded somewhere? So these are the basic 4 subsystems of the von Neumann model. So this is the diagrammatic representation of the computer, of the von Neumann model, rather. So I don't know if the screen is clear enough for you, but like I said earlier, if you're just joining us, the slides is already posted on the classroom, so you can go through it as I'm talking, and you can make sure you also go through it immediately after the class to refresh your memory about what I've said. So that way you can see, okay, so how much of what you've heard during the class will come back to you, and then you okay, I have to read more on this side and this side. That's a better way to study. So the computer, let's say the computer is that that big rectangle, and we see the inputs coming in from the left-hand side and the output coming in from the right-hand side. And inside that, you can see the input/output in yellow. You can see the memory, the arithmetic logic unit, and the control unit. So I believe now that, okay, if I tell you to describe the von Neumann model using a diagrammatic representation, I believe that by now you have a good idea of what I'm asking you, and then you have a good idea of how you would attempt to answer that question. So now let's talk about the input and output subsystem. So when we talk about input and output, this basically has to do with data coming in and going out. And when we talk about data, we need to talk about storage. So basically, disk is where the storage is done. So you store data, you store programs for processing, and sometimes you have sometimes the memory in a computer would not be enough. I'm sure you've experienced this using your own experience. So I don't know what the capacity of your phone is, because a phone is a computer, right? What the capacity of your laptop is, but sometimes you say that, okay, I need an external hard drive, or I have so many movies, I want to just keep it on the hard drive. I have a lot of this, a lot of that. You want to have like an external storage. So basically, that is the idea. So this diagram is just showing you that, okay, sometimes we have secondary storage devices, and you would see that even on your phone, you buy a phone, and then especially maybe Android phones, you have space to attach a memory card to supplement the data and the programs that are on your phone. Sometimes on your phone you see, oh, okay, your phone would prompt you to delete some apps. You know, an app is like a program. It's a set of instructions to carry out a particular task. So you can say that, okay, so both data and programs are what is stored on memory, both on your system, both on your phone. So data is different things. For instance, on your phone, data could be like pictures, it could be movies, it could be different files that you have, and it could also be different apps. So an app is a program. The same thing applies to your PC. So I believe that you are getting a clearer picture of how computers work from explanation, which is basically the whole point of this class. So, first program concept. That's the second idea behind the Neuman model, and this states that programs must be stored in memory. The program and its corresponding data. So again, this is just what I've finished explaining, meaning that your data and your programs are stored on your device. So the other idea about the Neuman model is the sequential execution of instructions. So all computers that you see now would execute the programs or instructions in a finite number and one after the other. So finite means, well, we already know it is not unlimited. We know, maybe, I don't know, if you write code, you know, okay, my code is maybe 1,000 lines or 20,000 lines. It is finite. It has a beginning, it has an end. And the control unit is now, I told you the control unit is the part that does the processing, the execution. So sequential execution of instructions is what is basically trying to explain to you what happens in your control unit. And the first thing is that it fetches one instruction from memory, it interprets it, and then it executes it. And then it goes back to the next instruction, and then it does the fetching, interpretation, and then it executes it, one after the other, for that finite number of instructions that we discussed about. So now let's go to computer hardware. So, well, computer hardware, sometimes we talk about computer, generally we talk about the parts, but there are some parts that, you can see and touch, and some parts that you cannot, really see and touch. So when we talk about memory, well, you can see the diskette, you can hold your flash drive, with your hand, but, there are some other things on the inside. So when you see your CPU, okay, this is the processor. Of course, you cannot really see the inside, which is all the things that we've talked about. So we were talking about, okay, what are the things that happen inside? So now we have an idea, okay, on the inside, we know that memory and data is loaded. So we know that programs and instructions are loaded in memory. We know that the CPU is what processes it, and then we know that the CPU does that by what now? By fetching, by interpretation, and then by execution, and then it gives the output. So now let's talk about data, storing data. So data is stored in form of electrical signal, especially this is usually done in binary form. So it's either something is, if you send a file now to your flash drive, and for some reason that flash drive is maybe problematic, so you would notice, okay, so it's either that thing is there or it's not there. So even when it's corrupted, you say, okay, fine, you cannot access that thing. So storage of data is in form of an electrical signal, and this implies that computer can store data in binary. So when you say binary, we mean two states, 0 or 1. So data organization now, although data should be stored only in one form, that is like binary pattern inside of the computer. Outside a computer, data can take many forms. We talked about this when I was telling you about data on your phone. So data can be in form of video or audio, it can be in form of pictures, it can be in form of text messages or text generally. You type something in your on your phone, it can be in form of numbers. But to the computer is storing it in binary form. So even your photo, if you go deeper, as you learn more in computing about digital systems, you know that even your photo, even though you're seeing it, or you're seeing somebody's head and all of that, a photo is stored in zeros and ones. So 0 1 0 1 0 1. If you have time, you can check this out. So how does the computer store a, a picture or an image? So everything is stored in binary form, which has been encoded in one way or another. We're still going to learn different types of encoding and how all this encryption is done. So how exactly is the computer processing audio? How exactly is the computer processing imaging? But now we're just talking about, we're just telling you that, okay, it is the binary pattern. In other courses, you're going to be learning more, you're going to be diving deeper so that you understand it. Remember, your understanding is to, build upon this knowledge, to survey, to, have your own ideas to it as time goes on as computer scientists and engineers. So now, in summary, requirement of a Neuman model is that the program must be stored in memory, and the program must be a sequence of instructions. So to depict that, this is our program and data in memory. So you have a box that this is memory. Know that part of that memory program is inside. Part of that memory data is inside. So let's say you want to add 2 and 5 together. So the data part will have the 2 and the 5. The program part will be the set of instructions that will fetch 2, interpret it, hold it, go and fetch 5, interpret it, hold it, go and fetch the instruction. Okay, add. Okay, this is the add is what now? It's an arithmetic instruction. So okay, so we are adding it, fetch that, hold it, and then do the processing, right? So the processing, 2 and 5 now gives you 7, right? So where will you keep that 7 again? You bring it back to the data part of the memory. So all these things, would be happening in the memory, and that is the whole concept that John von Neumann came up with, and now all systems work on it. So programs are essentially made of instructions. So this is how it works. So this basically is something like an algorithm or a flow of how a program works. So it consists of instructions. So you input the first data into memory. This is basically what I explained on the last slide. Get the first data in memory, get the second, add the two together, store the result and give an output of the result. So if you're a programmer, even if you're even if you're not a programmer, if you're a computer scientist, you should know what an algorithm is. So algorithm is a step-by-step solution. So this now 1, 2, 3, 4 can be described as an algorithm. So a programmer should, number one, solve the problem in a step-by-step manner, and then find appropriate sequence of instructions that solve the problem. So I ask you to write a program for me that will do this and this and this. So the first thing you should be thinking of is, okay, this is the problem. I need to find a solution to. What are the steps that are going to be involved in finding solution to this problem? That's the first task. And when you now find the solution, when you program in the specific language that computer understands. So now you have a solution to that problem, and the next thing would be for you to interpret that in appropriate sequence of instructions. So based on the language that you're using. So this step-by-step solution is an algorithm, and an algorithm does not really follow any language, meaning that I can say, okay, this step 1 that a program should do, that step-by-step is the algorithm part. So meaning that somebody
As the class ended, the lecturer has left. Oh.
Hello, I think, can you hear me? Hello? Hello,
Hello,
guys,
ma'am.
can you hear me?
We can hear you, ma'am.
Yes, I had some issues with my network. Can you hear me now?
Yes, ma'am. We can hear you, ma'am.
Okay, unfortunately, I'm trying to share my screen, but it's not coming up for me any longer. I don't know. How many of you have, do you have the slides? Can I keep talking? I can see it on my end, but I'm unable to share for now. I'm almost done with the class anyway. Okay, so I'll just keep talking, right? If you have the slides, please open it and follow along. As I was saying, I was talking about operating systems, and I was saying how it's like a manager that helps you to facilitate your computer, the components of your computer. Say you want to boot up your system, say you want a particular program to be installed. It is the operating systems, that would manage all of this for you. So I just wanted to, for you to mention that. And now I'm going to move basically to the history. If you have the slides, you'll see that the next thing is the history. So that's I'm on slide 29 now. If you're following, please follow on the on your own, so you can understand what I'm saying. So before 1950, we basically have mechanical machines, and it wasn't until the 1930s, between 1930 and 1950, that we had the first set of electronic computers. So we had ENIAC, ENIAC, electronic numerical integrator and calculator. So this is the first general purpose totally electronic computer that we had, and it was in the University of Pennsylvania in 1946. Remember what I said about what a general purpose computer is? How the program is already there, it's not flexible, it's just that's just one thing. All you have to do is bring in your data, get your output. So that first computer is called the ENIAC, and it's a general purpose computer. I said earlier I was going to give you an assignment for you to do some research. So how were computers, mechanical machines, what were they like before the von Neumann model? So that is your assignment. I'm going to post this assignment on the classroom so that you can also submit online. So that is the assignment. So I want you to go and find out and research. So how were computers before John von Neumann proposed his model? So in 1950, the preceding computers used memory only for storage of data. Remember I said that this was the very concept that John von Neumann changed by saying, okay, don't just use your memory for data, also use it for your instructions and your programs. So imagine now, let's say John Neumann did not bring in the new model, so your phone now would only be able to store data, and I mean your photos and videos and all of that. You would not be able to install maybe Microsoft Word for you to do this, maybe for you to type stuff off. Maybe you will not be able to install other things that you use to get things done. So it's just be for storage of data. So then we have the ED. We had ENIAC, which was the first general purpose computer in 1946, but now we had a first computer based on von Neumann's idea. And when I say von Neumann's idea, I believe that by now, if you've been following me from the beginning of this class, you'll know what I mean. So when I say what's John von Neumann's idea, you know what I'm talking about. So the first computer based on that idea, that concept, is called the EDVAC. So this is an idea. I'm sure you are familiar with this because this is usually taught maybe in secondary school or something. Like you have generations of computers and how they've been evolving to date. So it's important for you to know the history of computer. What was it like before, and then how has it transitioned over the years. Remember, this course is an introduction to digital computer system. You want to know where it's coming from. You want to know how it works. Basically, that is why you're taking this course. So as an introduction, the first generation of computer, you can see the year 1950 to 1959, like vacuum tubes. You can check online to see what that looks like. The second generation, the transistors, and they use high-level languages like Fortran and COBOL. All these have become outdated now, and we've moved to more sophisticated systems. So the third generation used IC, integrated circuits. So we had a mini computer, and it was in this third generation that the software industry was born. All the coding and the programming and all of that. It was, in the third generation, that's in the 60s, 1965 to 1975, that's, all the, integrated circuits and all that came about. And then in the fourth generation, like 75 to 85, we had the VLSI, microcomputers. So that's when the computers actually began to get smaller and smaller, and the circuits and combined, we started having micro, and getting everything smaller, and even running more things than it used to run before. So the fifth generation computer now consists of the laptops and the palm tops computer. So this is where we are now, and this is where you are now. So you're in the fifth generation. You're learning about computer systems, so that if there's anything, you're thinking, oh, okay, why can't they do this? Why can't they do that? You're free to innovate and make things better. Work on different parts. As computers are becoming smaller, there are new challenges, and that's life. But when something is evolving, some challenges that were not there will be there. So at least you can imagine in the days of vacuum tubes, we really didn't have, there wasn't really heating problems. But now you have packed so many stuff on the motherboard. So definitely you have to find a way to cool it down. You have to find a way to, you're making systems to be mobile. So you have to find a way to power them and make sure the power lasts, so you can see a lot of, that's why, when new phones come, they'll say, oh, this one, wireless charging, oh, this one, you can go for this how many hours. So research will now be going on in different areas. So you might not even, you don't even have to and what now? You don't have to come up with a whole new, oh, this is a new system. No, All the concepts are there. All the structure is there. So, but now there are different parts of it. So that is where you now begin as a computer scientist to find your own. Okay, this I find it really interesting. How the power and the energy part of computer systems. You can now pick that and begin to go learn more and innovate more. And then if you can get something done, something that can be better than what is on ground. You see companies like Apple. You can approach Apple. Apple, I have this, and then you become part of the team and you go from there. So before yes, this is the last slide. Before I end the class, I'm going to talk about microcomputers. So microcomputers are designed to be used by individuals, whether in the form of PCs or workstation or notebook computers. So that is what I was basically telling you, that now most computers have gone mobile, very, very mobile. So it's not something that you have to travel to your office for you to work, or you have to go somewhere for you to be. A motherboard now, a computer would contain both the CPU, the memory, the bus system, and the I/O ports. I'm not sure if of course, definitely you would see desktops where the monitor, that's the monitor, is an I/O, like is an input. You see it separate, and you see the keyboard is keyboard and mouse. There are also I/O ports. Like they provide inputs. Excuse me, they provide inputs for for the system. So I'm sure you have seen cases where all these things were separate before, but now a microcomputer contains all of this on a motherboard. So on your phone now, your screen, that is your output, your trackpad, that is your input, where you're able to swipe, you're able to type in something, is in one small device. Your bus system is inside it, where if you need to fetch something, one instruction from one program, you can just do that. All of it is there. Your memory system is there. I think Apple phones, they don't even have memory cards. So all the storage, everything is built in one system. And then the CPU, the processor, is also inside. So it's the one that runs, that computes. Sometimes you have 3 programs running on your laptop. Sometimes you have also on your phone, you have like 5 different things running at the same time. So your processor is managing all of that. You're asking for a photo to be brought up. You're checking your email on your browser. You're doing all of this at the same time. So a microcomputer is able to manage all of these things at the same time. So I've come to the end of this class. I want you to let me know if you have any questions. Do you have any questions? So now, in your exam, define the Neuman model with its name and the components and all of that. What is it about? Define and describe the stored program concept. What is that about? Describe the sequential execution of statements in the program. You should be able to do that using the appropriate diagrams. And if you need, I've also attached additional video on the Google Classroom, so you can read the slides, watch the videos, and have a better understanding. So if you have any question, you can also drop questions on the Google Classroom. Please unmute your mic and talk. Let me know how you found the class. Let me know if you have any questions. Hello? Hello?
Compared to other classes, this is better.
Are you there? I can't hear you. Who's talking now?
Yes, ma. I said compared to other.
Akban.
Yes, ma.
Okay, I'm listening to you.
I said compared to other classes, this class is better, ma.
Okay, I don't think I've taken your other classes apart from last week, but thank you. I'm glad you find it better.
No,
Do you have any questions?
no, I said
Questions?
not really, ma. So like compared to the other lecturers like that have taken us, I think this is more explanatory. Ma.
Okay, okay. Clear. Got it. No questions? All right. In the absence of any question, I would like to end this class now. Thank you so much for coming, and I wish you all the best. So, the class rep is the class rep here, Samuel. Please see me so we can fix another class for Monday. I want to fix 2 classes for next week. Is that okay? Please let's talk after the class. Thank you so much. Do have a lovely weekend ahead. Bye for now.
Bye.
Bye.